Hi, in this video, we want to talk about generalized linear hypothesis testing in regression. Okay, so usually in regression, we look at the hypothesis test that the either individual coefficients are equal to 0 or not, or we look to see if we have a good solid overall model with the F-test. All right, so here what we want to do, we want to look at a linear transform on our beta vector. All right, so here, let's say that C is a known matrix, and we're going to multiply it by the true coefficients of our model. All right, so C is a known Q by K plus 1 constant matrix. So remember that we have K predictor variables and the plus ones for the intercept. And we're going to say that C has full rank. So the rank is Q, and Q is less than or equal to K plus 1. All right, so let's think about some special cases about this. So first and foremost, we can think about the hypothesis that beta 1 is equal to 0 or beta 1 is not equal to 0. And in this case, what we're doing is, we are looking through to see if is this vector overall equal to 0. And here, if I'm looking at beta 2, actually looking at this, I think I switched. I think the 0 and the I need to be flipped on this, but conceptually you can follow it. All right, then for beta 2, this is if I want to look at the reduced model situation, I'm looking at this. So so we are in this hypothesis test, we're checking to see, do I want to drop these predictor variables, the corresponding predictor variables? Here, we're looking to see, is there informative value within these predictor variables? Now, why would we want to do this? Well, a good reason to do this would be for, this is really just a generalization of our F-test, checking to see, is there informative value in our linear model as a whole? This is an extension of reduced model hypothesis testing. But furthermore, if we think about it, we can actually look at this as ways to do feature engineering. So let's say that I have a bunch of predictor variables that have like similar measurements. So let's say I've got 3 test scores. Now, in my linear model, I could use each of, and we're going to use test scores as predictors. Each of the test scores could be an individual predictor. Well, another option would be to take the average of the 3 test scores and use that as a predictor. Well, if you think about it for a moment, taking the average, the arithmetic average, is just addition and dividing by a scalar. All right, so we can represent that with a matrix. Well, so that means that one of my possible feature engineerings would be to replace those 3 predictor variables with the mean, the row mean of the 3. And this gives us a way of tackling this. All right, so, and also this gives us the option of testing to see, should we do dimension reduction? Remember that principal component analysis is really just a special factorization of matrices. And we can always pull out what the matrix would be if we want to do that with our PCA. All right, so let's say that this is our model, that y is equal to intercept plus first predictor variable times beta 1, second predictor variable times beta 2, and then the random term. All right, so now, what if we were to run the hypothesis that beta 2 is equal to -2 beta 1? All right, so I'm just throwing this out. There's a bunch of different ways we could do this. Well, that corresponds to 2 beta 1 plus beta 2 is equal to 0, right? And so then I can rewrite this in terms of matrices. So we can see that C is the 2, 1 row vector. All right, now, if we fail to reject the null hypothesis, then I know that this beta 2 can be represented, it can be replaced by -2 beta 1. Okay, well, if I look at this, I could factor out the beta 1. And so then here, I could see that a good way to do feature engineering would be to take x1 minus 2x2. All right, now why would we want to do this? Let's say that when I look at x1 by itself and I look at x2 by itself, they're really not giving me that much correlation. And I might actually be better off putting them together to get a more reliable model. Now, usually we would be doing something like taking the average of the two. That's distinctly possible. That would work out nicely. And so if I was to replace my two predictor variables with x1 minus 2x2 to get a new predictor variable x new, this could be my model. And that might actually be a better model to work with. And if I was to use row means to get my new predictor variable, there can be some serious advantages with that dimension reduction. Less variance on the coefficients, and things are just more stable when we work with means if we can. All right, so let's take a look at a theorem. Let's say that y is multivariate normal, and the mean is x beta, and the covariance matrix is I times a scalar. Then C is a Q times K plus 1 constant matrix, and we've got full rank, and we have fewer rows than columns. Then C times beta hat is also normally distributed, but different dimension. Expected value of C beta. And then our variant matrix is going to be very similar to what we would expect it to be, but so we get the X transpose X inverse, and we get the sigma squared like we expect, but you can see that we've got C and C transpose on each side. All right, so now if we were to look at the sum of squares H divided by sigma squared, we can see that this term here, this whole mamma jamma, is going to be chi-squared distributed with Q degrees of freedom and non-centrality parameter of lambda. All right, so this is on the left, we have C beta hat transpose. On the right, we have C beta hat. That should be familiar. And then we have that covariance term, except for the sigma is missing. And then divided by sigma squared. And then here, this looks very similar to the other non-centrality parameters that we've talked about so far. Then if we look at our sum of squares error, then we're going to have y transpose and y on each side, and then I minus the hat matrix divided by sigma squared. And this is going to be chi-squared distributed with n minus k minus 1 degrees of freedom and 0 non-centrality parameter. But wait, there's more, because these are going to be independent of each other. Okay. So really, this just follows directly from the theorems that have already been presented in the textbook. So we have beta hat is multivariate normally distributed. That follows directly. We've got mean beta, and then we've got the X transpose X inverse times sigma squared for our covariance term. Well, so if I just apply the formula for how that we get this, if we take the expected value on this using this, we know that we're going to get exactly what we want. And if we take the covariance on this, remember that we're going to have a C and a C transpose popping out on each side, and then we factor out this. We take the covariance of the middle term, and then the sigma squared comes out. Easy peasy lemon squeezy. All right, and this is exactly what I just articulated, that anytime I have matrix times a random vector, we take the covariance, the matrix comes out front, boom, and then it goes to the back as a transpose, and then I get the covariance of beta hat inside here, and then we factor out the sigma squared and get it. All right, and so now, but wait, there's more, because if I go through and I apply what we've got going on, if we just write out the theorem, we're going to see that we take the appropriate, it is constant times the covariance matrix. If that's idempotent, then it ends up that we have a chi-square distributed, and it's an if and only if statement. And so we just applied that theorem. I think it's in 5.5, and boom, it comes out directly. 8.1 gives us the next part. What was the next part? The next part was sum of squares error. Yeah, this has already been established pretty well at this point. And independence just comes from the fact that beta hat and sum of squares error are independent. And so any function on those are also going to be independent. as long as things are broken up correctly. All right, so now we want to talk about the general linear hypothesis test, where the null hypothesis is that C beta is equal to the 0 vector. All right, so we're going to let Y be normally distributed, multivariate normal, expected value x beta, and covariance of sigma squared times I. C is a constant matrix, and its dimensions are Q, K plus 1. Q is less than or equal to K plus 1, and we have full rank. All right, we're going to say that beta hat is the well-known coefficient estimator, and we're going to take F to be SSH over Q, SSE over N minus K minus 1, which we rewrite like this for the situation. And then if the null hypothesis is false, then what's going to end up happening is that this F statistic is going to be distributed with F non-centrality parameter distributed. And here's lambda as the non-centrality parameter. Should look familiar at this point. If the null hypothesis is correct, then this F statistic is going to be F distributed, and it's going to be regular vanilla F distribution. So we just have to have the degrees of freedom. And there's the non-centrality parameter is equal to 0. So we just don't write it because we're lazy. All right, so if we want to take a look at the general linear hypothesis test, C beta is equal to 0 is the null, and the alternative is C beta does not equal 0. All right, we're going to reject the null hypothesis if we get a large F value. So if I think about that, then SSH over Q is much bigger than SSE over N minus K minus 1. So large F leads to rejecting the null hypothesis. I know that's shocking. All right, now something to think about. When we think about the non-centrality parameter, remember that we have positive definite going on in this with the x's, and correspondingly, putting a C on each side isn't going to change anything about that. So we have positive definite on this term. Therefore, we know that our non-centrality parameter has to be greater than 0. Positive definite. Okay, so the expected value of SSH over Q is going to be sigma squared over all this stuff. All right, this part here has to be, so we got positive definite going on with in the middle, and then C beta is going to be a vector. So that I know that this part has to be positive. Since it has to be positive, I know that this has to be greater than, or it has to be greater than sigma squared. My family are on the other side of the camera, and they're distracting me, by the way.
Hi.
All right, and now the expected value of sum of squares error over N minus K minus 1 has to be equal to sigma squared. Okay, so if I think about that, if I think about this on top of that, the fraction here over the fraction over there, I've got all this junk on top of sigma squared. And that's not exactly true because here I've already taken the expected values, but conceptually, like we know that, the ratio that we're getting from the fraction on top of the fraction, first of all, it has to be greater than or equal to 1. The only time it can be 1 is if this part's equal to 0, which might be with like from the beta is equal to 0, stuff like that. But so what we're looking at is if H naught is correct, then the lambda is equal to 0, and the lambda being equal to 0 is going to lead to this part being very small. So we're looking at F being not much bigger than 1 when we run our hypothesis testing. If H naught is incorrect, we're looking at lambda being significantly bigger than 0, and we're looking at this expected value to be substantially bigger than this expected value. So we're looking at having an F statistic substantially bigger than 1. All right, now, something that is very nice for us is that F-statistics are invariant to full rank transformations on X and Y. All right, so that means that what I can do full rank transforms all I want, let's say like with PCA, or if I want to do something like rescale, that's perfectly fine. My F-statistical stay the same. All right, so here's a theorem. If Z is equal to CY and W is equal to X times K, K is a transforming matrix, K is non-singular, so it's a square matrix, by the way. C is not equal to 0, then F is unchanged by these transformations. So if I run the F test, or the F statistic, based off of Z or Y, W or X, either way, I'm going to get the same statistic. So this is nice. This makes it easier for us when we start like doing our variable screening using center scaled versions of our data. All right, so recall that fitted values are invariant to full rank transformations. All right, if the fitted values are invariant under full rank transforms, and now that's transformations on X, then the sum of squares error is invariant under full rank transformations of X also. All right, so that means that SSE is equal to this. Now, if I take a moment, I can rework my betas so that beta hat W, and W is going to be equal to beta hat times X. All right, so I can match that up. So that means that either version is going to work out for me all I want. All right, so we're gonna alter C so that we have the corresponding hypothesis test on W after we change X. So if we think about the matrix algebra for a little bit, I can choose X so that, or excuse me, I can choose C, the constant matrix working on W, so that I get, in reality, the same hypothesis test as I would if I'm working on X directly. So I have a particular hypothesis test I'm interested in. All right, so we're going to say that C beta hat is equal to C K K inverse beta hat. All right, what we're going to do, we're going to set CW so that CW times beta hat W is equal to C beta hat. Okay, so W is equal to X times K. And so W K inverse is equal to X. And we can use this to get what we want. And then CK, we're going to say, is equal to C times K. Boom. All right, so now what I need to do, I need to work out the core aspects of the F distribution, or the statistic for the F test. All right, well, all I do is I just drop in all the parts for the new version of the hypothesis testing. Boom. And now I just start reworking it using matrix algebra. Easy peasy lemon squeezy. Okay, so I get all this stuff going. And I'm going to replace, every time I see a CW, I replace CW with CK. Whoops, oh wait, how did I do that? All right, so CW beta hat W is equal to C beta hat. So these two parts come from this equation here. Now, CW is equal to CK. So this CW becomes a CK. This CW becomes a CK. Now, W is equal to XK. So I'm going to, every time I see a W, I replace it with XK, XK. All right, so now I've done my substitutions. Let's just start reordering things using the operations we've got. All right, so transpose, remember transpose change the order. So I'm going to I can rewrite this as K transpose X, K, then big inverse around it, boom. And then this stays the same, and I switch the order on the transpose here. All right, now, what I'm gonna do, I look at this inverse. Remember, if I'm doing inverses, the inverse of something like this, I can, if I reverse the entire order of everything, I can replace it with the inverse of the individual parts. So it's like this K becomes K inverse. This parenthesis gets its inverse. This gets its inverse here. All right, so now at this point, I've got K and K inverse. Those cancel. I've got K transpose inverse, K transpose. Those cancel. All right, so now I've got this here. And I go, hey, that's the same thing we had a moment ago. Therefore, we see that the F statistics that we get, either way, it doesn't matter. Whichever presentation we use is going to work out as long as the transformation is full rank. Now, that shows the result on the X's, on the predictor variables. We don't have it for the Y's yet. And for the Y's, we just say that Z is equal to Y, and you just do some, if you just do some little tinkering factorization, it comes out. It's simple. Just replace the Y's with the appropriate, Z over C, and everything will just like clear out the way you want it. All right, so this theorem, the F test for C times beta equals 0 for general linear hypothesis testing. This is actually a full reduced model hypothesis test. So really, we're doing the same thing that we were doing when we looked at full versus reduced models. It's just a little bit more general. It's a little bit juicier. And the proof is left as a homework problem. It's long and tedious. I worked through the details of it, and it's not hard. I don't think it's very insightful, so I'm going to skip it. It's one that if you're not comfortable slugging through like lines of equations, you really should do it. It's good practice, good experience. I won't go far enough to say it builds character, though. It won't build character. All right, so now here's a theorem for us. If C times beta is not equal to 0, then this estimator, which is in the proof for this theorem, this is a biased estimator, but the variance is less than the variance of beta hat. All right, so if we take the expected value on this, we're going to get this as the expected value. All right, well, that's beta plus some junk. All right, that means automatically it's a biased estimator. If I take the covariance of it, I'm going to get the covariance of beta plus some junk. Now, if I take a moment, I'll look through here and I see, hey, I've got some positive definite aspects going on. And I realize from staring at this long enough that in reality, what's going on is that positive definite is going to make it, all the matrix multiplication turn into something positive. And so then what will happen is by subtracting off something positive, I'm getting less variance than I would otherwise. All right, that's all I've got for you. Take care and goodbye.